So our next session, this session about OpenMP tool support, it's going to start with the presentation from Vladimir Indic. Indic?
Thanks. That was a good one, yeah.
Entitled Improving Tool Support for Nested Parallel Regions with Introspection Consistency. Please go ahead.
Hello, everyone. I would like to thank Sarah for the nice intro. And without further ado, I would start with a typical OpenMP program that exploits nested parallelism on a host side, shown in the diagram on the left. And as you may notice on the right, so basically the initial primary thread starts executing a code A, which is application code, encounters a parallel construct, enters runtime frame to set up this region, let's say creates a new team of threads. And when the setup is finished, basically it exits the runtime to execute the real code that belongs to the parallel region B. On the other hand, non-primary worker thread, in this case number 1, is initially idling for work, and in order to become part of the region, it needs to execute some runtime frames, like some runtime routines, and then exits the runtime to execute the application code of the region B itself. Similar process happens when this thread encounters a nested parallel construct C, basically enters the runtime, setups the region, then exits runtime to execute the application code. And as you may notice, the OpenMP application level context is distributed across multiple threads, and there is a huge semantic gap between like a source level view and the code that runs on the machine itself, like the implementation reality. So to bridge this gap in 2018, an OpenMP tools API has been developed and introduced in a standard. So it requires that a runtime maintains state for each thread so that the tool can detect whether a thread is doing serial work or parallel work or, let's say, idling for work. A tool should also be able to register to receive callbacks for important operations like parallel region begin and end, implicit task begin and end, so on and so forth. And for us, especially important is a subset of routines that can be used during a call stack unwinding so that a tool can detect on the fly the presence of all active parallel and task regions. So in order to get information about, let's say, existing regions on the innermost level, we can a tool can inquire the get parallel info routine with ancestor level 0. For outer levels, we can call this routine with, let's say, ancestor level 1, 2, etc. Similarly, is if we want to introspect information about tasking constructs. So the majority information are read-only by nature, so you can just read them. But the two of them are very important because a tool can use them to store some arbitrary value for some task or region during its existence. And they are called parallel data and task data. They are simply a 64-bit data word, and I will explain how the HPC tool can use that. So while we try to profile some programs dynamically linked to the newest LLVM OpenMP 5 with HPC Toolkit, we notice a few shortcomings of the implementation. So what HPC Toolkit is, it's a set of tools used for statistical sampling and profiling of the code that is able to build call paths that matches the source level view of the code. To do that, basically, when a thread receives a sample, it unwinds the call stack to capture the invocation context and then attributes the cost of that context. The first problem when trying to profile an OpenMP worker threads is that they can just do a partial unwind of the call stack because they don't know, like the invocation context of this region B, let's say, known only to the primary thread that creates the region. So that a worker can be able to get this information, it needs to subscribe to receive those kind of information. And for this purpose, what we did is we added some code that enqueues a request in a list, which we keep in a parallel data word of regions B. And this parallel data word is provided and maintained by the runtime for this region. So at the very end of the region, what a primary thread does is it checks whether there is any registered threads, like any subscribers. And if so, it unwinds the call stack to determine the invocation context, but without runtime frames, because we think they are unnecessary. What we notice is that there are two timing windows while thread creates or destroys a nested parallel region during which the OMPT get task info routine provides a wrong information about an enclosing region. And this results that a worker thread might not be able to always subscribe to receive information about all enclosing regions. To better understand this, we need to dive a bit under the hood and understand how the LVM runtime works. So basically, every parallel region is represented by a corresponding descriptor. In this case, we mark it as a team. This team descriptor contains information about teams, so what threads running this region, and other information about the region itself. There is a parent pointer to the enclosing team descriptor, if it exists. And there is a nested blue rectangle containing like OMPT descriptor with all the OMPT information about this region that can be acquired by the introspection team. Similar thing is with tasks. So for each task, runtime creates a task descriptor, and they are shown in the red. So assuming now that thread is executing region 1 and region 2, that are two nested regions, what happens when thread encounters another parallel construct? So first thing is that a primary thread assembles a team descriptor for this region 3, forms a new team of threads, and shares this descriptor with those threads. After that, each of the threads creates a corresponding task descriptor for the implicit task, execute the implicit task, enters a final barrier, destroy the task, and finally, the primary thread just destroys the team descriptor and returns to executing and enclosing context. The party starts with serialized parallel regions that are executed by one thread only. And for high performance, LLVM runtime provides tailored implementation. So the information about the innermost region, in this case, innermost serialized region, in this case, region 2, are present in the team and task descriptor as we showed on the previous slide. And these kind of descriptors are always allocated on the heap memory of the thread. However, the information about enclosing serialized region, in this case, serialized region 1, parallel region 1, are only OMPT information are present on the stack in a specially designed lightweight team script. So what happens now if a thread needs to create another nested serialized region R3? So the first thing that happens is we create a lightweight team descriptor for storing information about now an enclosing region R2. We copy team and task information from the heap to the stack. We reuse team and task descriptors, so we save some time to allocate a memory on a heap. And we reuse these descriptors for the region R3 because it shares the majority of information about the region itself. Only ICVs might be different. And what happens next is that we push this R2 LWT on a list of LWT descriptors. LWT list is just a pointer to the let's say to the newly created element, to the head of this list. So the main challenge that OMPT get task info and parallel info introspection routine faces with is that at an arbitrary point, a sample event can occur. So a tool can invoke introspection routine to inspect active parallel and task regions. So what introspection routine does is for the innermost level, ancestral level 0, it reads information from team and task descriptors, the regular one. And for higher ancestral levels, it either follows up the chain of team and task descriptors in the case of regular parallel region. For serialized parallel region, we read information from LWT list. Beside inspecting information about the regions, a tool can also update information in a 64-bit tool work. So what we found out is that if a sample arrives in the timing windows I mentioned on one of the previous slides, LLVM runtime fails to provide correct information, which might be a disaster for a tool. So the first failure that we encounter is if a sample interrupts the creation of regular parallel region after the moment when primary thread updates the team descriptor but does not update the current task descriptor. So what introspection routine does in that case, it reads information from current team and current time descriptor by they don't match. So it reads information about R3 team, R2 task, R2 team, R1 task, and so on and so forth. Even worse thing happens when creation of nested serialized region is interrupted because we are trying to copy information from two different places on R2 LWT. So introspection routine does not know where the information resides. And what can happen is if we provide somehow this team and task descriptor in that moment, even update might happen and the runtime might not see it because it already copied some information, so it can override and lose. So when we check the standard specification, it did not cover this case. It just guarantees like a weak property. So this means that information about an enclosing region may be reported as unavailable during the creation of nested region. So we think that's not good because there are some blind spots where tool might not know that an enclosing region exists, even though it's fully assembled and tried executing it for some time. So what we propose is an improvement in the sense of OpenMP introspection consistency that guarantees that a tool must receive valid and consistent information. So the first thing that we say is that any thread involved in a parallel region must be able to obtain information about parallel region itself from the team descriptor and its implicit task from the moment of implicit task begin on that thread until the moment of implicit task end of the primary thread. What this basically means is that it guarantees that information about the enclosing region will be available while thread is entering or exiting the nested region. And also, a thread must be able to obtain information about an explicit task from the time the task is scheduled for execution on that thread until the task suspends. So, how to provide introspection consistency for parallel region while creating a parallel region? It's simple. Just check whether the current team descriptor matches the current task descriptor. In this case, no. So just skip the current task descriptor R3 and provide information about R2 and R1. And this is okay for OMPT get task info because it does not need to provide information about the region that's not fully assembled yet. On the other hand, tricky part is how to provide information about nested serialized parallel region. So a trivial approach would be let's block signals while thread is entering or exiting the region. So introspection is not possible by a tool. However, this might introduce some significant interference with sampling that causes a tool to collect unrepresentative data. An alternative approach would be that introspection routines tries to detect when runtime is creating or destroying a region and finish up the region, finish up the creation or destruction instead of runtime. For these purposes, we develop a wait-free coordination protocol that guarantees that in a finite number of steps, either the runtime or the introspection routine will finish up with process of creating or destroying the region and deciding where the OMPT information resides. So for this purpose, what we did is each of the descriptor, each kind or type of descriptor, so team, task, and lightweight team descriptor, we extended with a pair of OMPT descriptors and a pointer that says which element of the pair contains valid information. So what this means? Information about the R2 team are present in the first OMPT descriptor, shown in blue. Information about the R2 task, in this case, are shown in the second descriptor, shown in red. And the information about the R1 are present in the first OMPT descriptor. So what happens now if we need to create a nested serialized region 3? The first step is to allocate lightweight team descriptor on a stack. Then what we do is we mark these two PTR pointers by setting the lowest significant bit to 1. What this says is we are just about to move information from this place. However, if a sample receives at this point, it's okay. Introspection routine just masks the pointer, reads it without the lowest one, and just read the OMPT information. And that's it. The next step is important. So in the next step, what we do, we also mark a pointer to this R2 LWT and replace it with a head of the list, which means that we push R2 LWT onto the list, but a head of the list is marked. This means if introspection routines is called, it can see that the process of copying information start, so it will help. The next step is that runtime does is to copy information from team and task to R2 LWT. And then we try to update the pointer of this lightweight team to points to this element by using a compare and swap. Why compare and swap? Because a call to introspection routine can interrupt runtime. In this case, it didn't, so compare and swap succeed, but if compare and swap fails, it means introspection routine finish up the process at the runtime, so runtime does not do anything more. And similarly, what happens next is we try to reuse information. We try to reuse descriptors for R2, R3 team and task on a similar way by using a compare and swap. And as the last step, we just remove a mark and saying, hey, everything is fine, so you don't need to bother about this edge case. Now it's complex, but that was the solution we found. So what happens with introspection routine? We need to introduce some more complexity there. So basically, if introspection routine sees that ahead of the list, LWT list pointer is marked, it will finish up the creation or destruction of the region by doing the same step as a runtime with a few differences. So we don't need to use atomic operations, so there's no need for compare and swap. Why? Because introspection routine is executed atomically with respect to runtime code. So runtime code cannot interrupt. And also we use the second OMPT descriptor when trying to update the PTR to ensure that an update of a tool data by introspection routine won't be lost. If, however, this LWT list is not marked, then do as before. Just read information from current team task descriptor or follow up the LWT list entries. So the question that arises is, will providing introspection consistency with our approach hurt overall performances? Why? Well, we made the script slightly bigger. We introduced an additional level of indirection when accessing the OMPT state, and the implementation of introspection routine is more complex. So our evaluation focuses on comparing different approaches, like 3 different approaches, for guaranteeing the introspection consistency of nested serialized regions. So what we compare in the evaluation, so we compare 4 different runtime implementation. The first one is basically a fixed or improved LLVM upstream that fixes the corner cases about creating the regular or serialized parallel regions. How? By saying information about enclosing regions are unavailable, so there's no introspection consistency, but that's fine. That's what's easiest to implement. Just take one if, and that's it. Other 3 approaches guarantees introspection consistency, and the W version uses our weight-free protocol. The F version removes lightweight teams from the story and uses like a full heavyweight descriptors allocated on a heap. And the last one is the B version, which is just adapted U implementation that blocks signals while thread is entering or exiting the nested region. So we conducted a few experiments on an idle machine at that time with Intel Knights Landing architecture. There's one processor with 68 4 ASNT cores to prevent unnecessary changes in coded data layout. We disable Linux address space randomization, and we build all 4 runtime versions with Clang 12, they show 3, and we enable OMPT support. I know it's a dinosaur, but we did. So we conducted 2 groups of experiments. The first one tries to stress test the runtime and see what are the performance in the worst case scenario, which means, so for these purposes, we developed like a serialized micro benchmark containing 1 serialized parallel region that spawns 60 millions of nested serialized regions that basically do nothing. So the majority of time, we're just executing the runtime. We just want to see what are the worst case performances. We build it with Clang-03. The other group of experiment focuses on checking whether the nested serialized regions are widespread in the real-world application. And for this purposes, we use a spec OMP that is benchmark suite with 14 representative scientific and engineering application code. We built it with Intel 16 because some of the benchmark uses Fortran, and we didn't have like a Flang on that machine at that moment. And we disabled proc binding, thread binding, because we noticed that sometimes when we enable it, the performances got worse on the machine. The following experiments consider each benchmark dynamically linked to one of the runtime libraries. U, W, F, and B, you will see the notation on the next slide. So the first experiment of the first group tries to measure the cost of maintaining nested serialized region in the worst case scenario. So what we did is we ran a serialized region, serialized micro benchmark instance, standalone dynamically linked to one of the four libraries. So U, W, F, and B. For 30 times, we calculated the mean time and the standard deviation. Running a benchmark standalone means the MPT support is compiled, but it's not used because we don't need to maintain information. There is no tool. And what we did is we calculated overhead of W, F, and B relative to U. So W, F, and B relative to U. As we noticed, the W and U are comparable. Although we measure some negative overhead, we don't say our approach is better. We just say that they are comparable. We can see that F version that uses like a heap allocation for heavyweight tasks introduce about 80% overhead. And what we observed also is that in order to block signals, we introduce some call to sigproc mask that changes the layout of the code and introduce overhead of 7.5% on iCache sensitive machine like a KNL. And we say that this might not be observed on other architecture with more cache per core. The second experiment tries to see what's the cost of maintaining OMPT information for this kind of regions. And because of that, we attach a trivial tool to activate OMPT information maintenance. A tool is pretty trivial, only a start tool, initializer, and finalizer, nothing else. And we again calculated overhead of W, F, and B to relative to U. We may notice that the overhead of W is 14%, which is 3 times less than the overhead of F. So we are still better than using a full heavyweight descriptors. And we can see that blocking signals for this short parallel regions can drastically distort the performance and introduce overhead of about 300%. The last experiment of the first group basically tries to see whether the complexity of introspection routine has any negative effects to statistical sampling. So we extended the simple tool with a signal handler that basically calls a get ask info for all available parallel regions. That's one of the steps HPC toolkit does, so we do the same thing. And the signal handler is pretty much called every 5 milliseconds. And right now we calculated overhead relative to trivial tool time. So so basically we compare this execution time with execution time here, this one with this one, and so on and so forth, just to see what's the overhead of sampling on top of OMPT information maintenance. And we found out basically that pretty much all versions have similar sampling overhead, so everything's okay. The last group tries to measure the runtime performance in real-world scenarios and tries to see how frequent are nested serialized regions. And for these purposes, we use runspec, which is some tool from a spec OMP benchmark. And we run each of the benchmark dynamically linked to one of the library for 3 times with reference workload and no tool attached. We find a median runtime and divide it by the reference system runtime. That's how the runspec does. It calculates a normalized ratio for each of the benchmark and calculates the geometric mean of all 14 normalized ratio. This means basically the higher number you get, that's the better. For UF and B, the ratio was the same, 4.23, so they are comparable. And we noticed some negligible drop in our wait-free implementation of 4.22. When we checked each benchmark standalone, we find out that using our approach when running a benchmark with a lot of short nested tasks, however, has some 3% overhead. Although our code is not called when creating a task, it obviously changes the code layout a bit and causing some more branch and iCache messes that we observed with perf. Overall, the conclusion from this group of experiment is that nested zeros regions are not widespread in the real world application, so there might not be benefits of the complexity that our approach introduces. And for the end, I would like to say that from a practical experience with LLVM OpenMP 5, we noticed some shortcomings of the current implementation and some weak specification of the standard. So we propose some improvements by introducing introspection consistency. This is just some kind of a semantic changes to the standard. So not anything drastic, just to semantic state what can tool expect in some situation. So we don't need to handle all those edge cases in the tool itself, but to have some guarantee for the tool. And basically, we set up a firm foundation for reliable OpenMP tools to build. We develop a novel implementation of wait-free coordination protocol that provides introspection consistency at some reasonable cost. However, it has some complexity. And what we can see is that our approach can be applied in a more broad, more general context. So basically, whenever runtime, so whenever a program manipulates data that a signal handler can inspect and change at any time, we handle as a data race between the runtime and signal. And I would like to thank for your attention, and I would be happy to take your questions.
Thank you, Vladimir. Is there any question from the audience? I think there was, okay. Deepak.
Thanks for the talk. Could you state again, maybe simply what you would say are the semantic clarifications that you would like to be?
So I step out that slide. Basically, what we want to say is that when a thread is involved in a region, so after implicit task begin of that thread, so after that event, basically a thread is executing the code of implicit task of that region, it should always provide information for that region. No matter if we enter some new region or whatever, this region is still active and some present on the stack. Until when? Until the primary thread basically executes the implicit task scan, which we can consider as basically the region end. Because a thread, so a worker thread can, as far as I know, the order of the events are implicit task end of the primary thread, and then a parallel end. And the worker thread can see implicit task end at some other point while trying to be employed in a new region. And something similar we state for a task. So when a thread is executing a task, you should provide information about it. So after you fully set it up, you the runtime should provide information about that task or region. Basically, that's it.
Is there any other question? No. I actually have a question myself. When you started the evaluation, you showed different overhead measurements.
Mm-hmm.
And there was a significant difference between the first one and the second one.
Here or here?
Between this one and the previous one.
You mean the F version?
Yeah. So I didn't really get why. So
here's the
difference.
thing.
I mean, F is so bad here.
Yeah, and that's a good question. I skipped this part because I didn't want to deep dive into the complexity. So basically, the U version has execution time of 8.9. And here it has execution time of 10.9, which means that by attaching a tool, you need to have some overhead for maintaining the information about the MPD itself, which means that lightweight task descriptors are initially heavy. They introduce 20% on top of that. And basically, the F version does not have lightweight task support, which means that when you enable when you attach a tool, you don't need to do anything additional than the overhead here. So basically, if you increase the overhead of U and don't increase the overhead of F, then the relative overhead will drop down. Sorry. Yeah, so sorry for that. Like about 9 seconds, we are executing without tool in the U version, and 11 seconds when we attach a tool. So U needs to maintain like 280 teams, and that costs 20%. However, F does not need. So basically, you can see 16 seconds here and 16.2 seconds. So relative overhead drops down, but absolutely pretty much.
Okay, thank you.
Thank
you, Vladimir.
Well, I don't know.